In the last tutorial, I made an assertion that it was surprisingly easy to translate the P5 JavaScript code into Game Zero Julia code. For this tutorial, I'm going to test that assertion by attempting to clone a flocking simulation created by Dan Schiffman using P5 and JavaScript that he posted on his YouTube channel, The Coding Train. Will my amateur attempt end up on a Respect compilation? Or will my shameful failure be featured on an Instant Regret compilation? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
The first time I saw a flocking simulation video was just a few months ago. I remember thinking at the time, it's amazing what you can do with computers today. You can imagine my disappointment when I learned that the flocking simulation algorithm has been around since the 1980s. Which just goes to show you that I've been living under a rock for the past 35 years. The flocking simulation was originally developed by Craig Reynolds in 1986. It's also known as Boids, or the Boids algorithm, and it's an artificial life program which simulates the flocking behavior of birds, fish, and other wildlife. By the end of this video, you'll be able to create your own flocking simulation. For this tutorial, knowledge of Julia and VS Code is required. I'm also assuming that you watched episode 409, which gives an introduction to the Game Zero package. Okay, let's get started. Let's jump right into VS Code. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called rungame.jl. Also in the tutorial folder, create another file called boids.jl. Launch the Julia REPL by using Alt-J, then Alt-O. Maximize the terminal panel. Change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the Game Zero package as well as the colors package. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. Minimize the terminal panel. As with all of our previous Game Zero projects, we start by initializing the game window. You can change the dimensions to fit your monitor. Next, we're going to set up our actors, which we will refer to as boids. The term boid was used by Craig Reynolds to refer to what he calls the generic simulated flocking creatures. Boid is a shortened version of birdoid object. In other implementations that I've seen, boids are represented by directional triangles, but for our simulation, we'll be using colored circles. We've used all of this code before, so there's nothing new here yet. Let's take a look at what we have so far. In the rungame.jl file, enter the code to run your game. In the game window, you should see 200 red, green, or blue dots scattered randomly on an antique white background. Each dot represents a boid that we will set in motion with our code. Next, we need to set up vectors to hold the initial velocities and accelerations for each boid. Each boid will start with a random velocity and direction, but with zero initial acceleration. The acceleration will be determined by three behavior rules that will generate a so-called steering force. We'll discuss these behavior rules and steering forces in detail in a few minutes. Unlike in previous tutorials where we try to contain our actors within the game window borders, for this simulation, we want to give our boids the freedom to travel as they please. By using this code, if a boid wanders off the edge of the game window, it will simply reappear on the opposite edge. Next, we need a function that will calculate the distance between the centers of two different boids. The Game0 package does contain a function called distance, but it only contains methods to calculate the distance between two image file actors, or between an image file actor and a point. Since it doesn't contain a method to calculate the distance between the center points of two circles, we need to extend the function by creating our own method, which is just the Pythagorean theorem. One of the challenges of using Game0 is that since it uses raster graphics, you need to convert your calculations into integers in order for Game0 to draw your actors in the game window. Otherwise, you'll get an error message. As a result, you'll be using the round function and the integer constructor a lot in your Game0 code. For our final setup, we need to set up some variables that we can use to fine-tune the behavior of our boids. We'll discuss these variables in detail a little later. Now, it's time to create the function that will breathe life into our boids. On his website, Craig Reynolds states that his basic flocking model consists of three simple steering behaviors, which describe how an individual boid maneuvers based on the position and velocities of its nearby flockmates. He calls the three steering behaviors separation, alignment, and cohesion. Separation is used to avoid crowding local flockmates. Alignment is used to steer towards the average heading of local flockmates. And cohesion is used to steer towards the average position of flockmates. When following these three rules, each boid is only influenced by the flockmates within its limited neighborhood. The variable named perception_radius is the radius from the boid's center point, and it defines the boid's local neighborhood. We're going to create a single function that contains the logic for all three behaviors. This first part initializes the arrays that will be used by each of the rules. Next, we create a nested for loop to compare the attributes of each boid versus the attributes of every other boid. Next, we add a conditional statement so that we only focus on the boids within the neighborhood. We start by populating the attribute arrays for the other boids inside of the neighborhood. The variable named separation_force is just the distance between two neighboring boids in both the horizontal direction and the vertical direction. The variable named neighbor underscore v is the velocity of one of the neighboring Boids in both the horizontal direction and the vertical direction. The variable named neighbor is just the x and y coordinates for the center point of the neighboring Boid. And this just increments the counter. Now, we add another conditional statement that will apply the three rules if there are any other Boids within the perception radius. Inside of this conditional statement is where we will place all of the code for the three steering behavior rules, starting with the separation rule. The first step to implementing the separation rule is to calculate the average distance between the Boid and its neighbors. Now that we've calculated the average, we use this average distance to come up with a so-called steering force, which will steer the Boid away so that it can avoid colliding with its neighbors, which is why this behavior is called the separation rule. That variable named separation underscore dial can be used to either strengthen or weaken this behavior rule by changing the value that we set up initially. This is a subjective setting. I set it at a level that I like, but feel free to experiment on your own by using different values for the separation dial. In order to regulate the velocities of the Boids, we're going to use minimum and maximum speeds. This will help to make your simulations more fluid by avoiding sudden rapid accelerations or decelerations. After coming up with a steering force, then we simply insert it into the Rx1 and Ry1 arrays. Once completed, these arrays will contain the acceleration value for each Boid in order for it to follow the separation rule. And that's it for the separation rule. My code is not a line-by-line copy of the code from the coding train video. I've modified my code slightly in order to make it work with Game 0 and with Julia. I think that I've captured the essence of the code from the coding train, but my code is not meant to be a literal translation. If you're interested in seeing Dan Schiffman's original JavaScript and P5 code, I have provided a link to it in the description below. Okay, the next step is to add the code for the alignment rule. The first step to implementing the alignment rule is to calculate the average velocity for all the other Boids within the neighborhood. Now that we've calculated the average, we use this average velocity to come up with the steering force for this alignment rule, which will steer the Boid in the direction of the average velocity vector of its neighbors. Just like before, you can change the value for the alignment dial variable in order to fine-tune your simulation for this behavior rule. Also like before, we use minimum and maximum speeds in order to regulate the velocities for the Boids for this behavior rule. You can copy and paste the code from above and change the 1 to a 2. Finally, once we come up with a steering force, then we insert it into the Rx2 and Ry2 arrays. Once completed, these arrays will contain the acceleration value for each Boid in order for it to follow the alignment rule. And that's it for the alignment rule. The next step is to add the code for the cohesion rule. The cohesion rule is the opposite of the separation rule. While the separation rule steers the Boyd away from its neighbors, the cohesion rule steers the Boyd towards its neighbors. This combination of seemingly contradictory steering forces leads to some fascinating movements. The first step to implementing the cohesion rule is to calculate the average position between the Boyd and its neighbors. Now that we've calculated the average, we can use this average position to come up with a steering force for the cohesion rule, which will steer the Boyd in the direction of the average position coordinate of its neighbors. Like before, we use minimum and maximum speeds in order to regulate the velocities of the Boyds. Finally, once we come up with a steering force, then we insert it into the Rx3 and Ry3 arrays. Once completed, these arrays will contain the acceleration values for each Boyd in order to follow the cohesion rule. And that's it for the cohesion rule, and that's it for the flock function. The next step is to define the update function to set our Boyds in motion. Just like we did in the last tutorial, we use the update function in Game 0 to move the actors in the simulation. The first step is to call the flock function that we just created. Next, we set up a for loop to update the positions for all the Boyds. The first line in our for loop calls the border function that we defined earlier. Next, we need to calculate the acceleration for each Boyd, which is just the sum of the vectors for the three behavior rules. Next, we use this acceleration to update the velocities for each Boyd. We do one final check for minimum and maximum speeds. Once we have the final velocity, we update the Boyd's position. One last step that we need to do is to reset the steering force vectors, so that the values of the steering forces do not accumulate over time. And that should be it. Let's take a look at our simulation. Save your file and go back to the rungame.jl file and rerun the simulation. Fascinating, right? My model looks more like a school of fish rather than a flock of birds, but it's interesting nevertheless. You can definitely see all three rules in action. Over time, the Boyds are definitely aligning with their neighbors, and they're engaged in this interesting dance where they're simultaneously attracting to each other, while also repelling from each other in order to avoid collision. If you'd like to see a sophisticated version of the flocking simulation using Julia, check out Jesse Battencourt's JuliaCon 2020 presentation, where he demonstrates his implementation of the flocking simulation using Mach-E. There's also a Julia package called agents.jl, which comes included with a flocking simulation model already built in. I know that these boys are not alive, but because they're following rules, their movements resemble intelligent behavior. It makes you think, doesn't it? Is that all life is? Just following a set of rules? Is it possible that we're just boys following a set of rules in a simulation of our so-called life? Believe it or not, we've come to the end of this tutorial series. So if you made it this far, congratulations! There is one more tutorial for next week, but it's a final project to wrap things up. This was a very interesting project for me to work on, and I hope that it was interesting for you as well. A year ago, I was just starting out on my Julia adventure, so there's no way I could have done this last year. It hasn't been easy, but I can definitely see some progress in my coding abilities, and I hope that you're seeing progress in your abilities as well. For those of you who have been with me since the beginning, thank you for coming along and sharing this journey with me. I would especially like to thank all of my channel members. Your support makes these videos possible. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.